All right. Yeah, so thanks for having us along. I guess what we're doing with our product is tackling carbon emissions in another way. We're not changing the concrete. We are reducing the amount of concrete by using void formers. We started the business in 2018, Scott and myself, and yeah. So if you look at the zero waste hierarchy, the best things are often to rethink, redesign, reduce amount of materials to begin with, or even reuse structures. And further down the pyramid, you then look at using recycled materials or recycling, and then landfill is the sort of thing that you do at the bottom. So our solution tries to work up the top of the pyramid as much as possible. So we're about reducing the amount of concrete. But we also use recycled material as well to facilitate that. Yeah, so just quickly, I'm the inventor of the product, and it's sort of evolved through my history in engineering. I've worked in Melbourne, Canberra, Sydney, Dubai, and London on various types of structures across a lot of different sectors. And in the UK, I was with Laing O'Rourke for 13 years, I think it was. And I was their main product developer for precast concrete elements. And so I was heavily involved in the development of their new factory, their component set of products, which was all about DFMA and producing quicker, more efficient construction. And types of products we used were things like twin wall. And so, yeah, we worked out how to use twin wall for big, large water tanks instead of using in situ concrete. So we could build those projects typically 30% faster with half the amount of people on site, a lot of quality benefits and health and safety benefits. I invented the floor system on the cheese grater building in London. So that was originally a metal deck solution with in-situ concrete. And I invented this flooring system, which was installed for 40,000 square metres on the project, just by 2 guys on site. The good thing about that was very quick and not much labour required on site. All the work's done in the factory, or as much as possible. And then another system I invented subsequent to that was another floor system, and that involved the use of headed anchor bars projecting from planks and a very efficient connection method. So the previous one was patented, and this one's also patented. So it's been used up to 30 stories in the middle of London. And with that type of construction, you can build a new floor every 3 days. So it's very quick. So compared to in situ construction, that's about twice as fast. So after those sort of experiences, I started thinking about how can we do the same thing but more sustainably. In particular, I was looking at 3D printing and thinking about what geometries we could create to do something smart with structures. And I came up with this cone type of geometry, which has got different heights, and it's got a square base, 200 millimeter square, and it's designed so it clicks together a bit like Lego. And you can create void formers, so you can reduce the amount of concrete in structures. So the first thing we do is we reduce the amount of concrete. We take out the concrete where you don't need it in the structure. This is often the case in floor systems. When any element that is bending, like a retaining wall or a floor that's bending, you mainly need the concrete at the top and the bottom of the slab where the higher stresses are. And so you take out the concrete from the middle of the slab as much as possible. And then the thing that's a little bit unique compared to other void former systems is you can use the void to create strong and fast connections between elements. So that's the second image, where we fill the void locally with in situ concrete and some reinforcement bars, and that gives us a nice strong connection. The third thing we can do is fill the void with insulation, and we can actually use it for facades of buildings and get very thermally efficient buildings. Yeah, so just to illustrate how that void forming process works, the red arrows, if you follow the red arrows, that's where the concrete gets poured in from the top. It flows down through the cones, the recycled plastic cones, and spreads out underneath. Fills up the cones and it spreads out on top. So the void that's left is in between the cones. And typically we can reduce the amount of concrete by 30%. And as a result, the CO2 emissions reduce. We have less weight on the building. And when you're delivering the precast elements to site, there's less deliveries and smaller cranes required. The yellow arrow on the top is pointing to a solid rib of concrete. We leave solid ribs of concrete between the void formers where we need it for shear strength. So engineers can just design that rib according to the codes for shear strength. And you analyse the slab a bit like an I-beam. So you have a top and a bottom flange, and then you have webs for the shear. This is a close-up detail of the joints. I'm just showing how you can fill up the joints locally and put bars in the joints to create strong connections between panels. By having this type of efficient connection, that allows the fast construction to happen because there's very little in situ concrete required on site and very little work to do on site. You just place the planks, slide the bars across and fill it up with concrete. Yeah, so the good thing about using this in precast elements, you get higher quality, you reduce the on-site labour and waste associated with in situ concrete, and it's a lot quieter and cleaner in terms of the impact on neighbours. In terms of the manufacturing of our product, we're currently producing in Melbourne. We can make about 40,000 square metres of product per year. The injection moulding machine you see on the left produces 2 cone shapes every 20 seconds. And we then click the parts together to form these boxes, the void former boxes, which you can see on the right, which we deliver to the project or the precast factory. Our production facility is solar powered. It's not always 100% solar, but we have solar panels on the roof, and the energy we get from the grid is also there's a higher percentage of solar in that, particularly when we're producing during the day, when there tends to be an excess of solar power in the grid during the warmer months in particular. So that allows us to produce the product with very low carbon embodied emissions. So roughly for every 1 kilogram of embodied emissions in our product, we can save about 30 kilograms of CO2 emissions in the concrete structure. Oops. So this shows it going into some production at a precast factory. The mesh goes down, you put the void former boxes on top, another mesh on top, you pour the concrete. And on the right there you can see the how there's a void created in between the cone shapes. We have little holes in our product that allows the air to escape, so you get good compaction. You end up with a little bit of seepage, but not much. Well, that's just a diagrammatic representation of that process. This is an example making retaining wall elements. These are 6 meter high retaining wall units, and the void formers in this case reduce the concrete by about 40%. So instead of delivering a 20-ton unit to site, it reduces to about 14 tons. So you can fit two of these on a truck instead of one, as well as the CO2 benefits. There are also some savings in reinforcement for shrinkage reinforcement, because that requirement is proportional to the cross-sectional area of the member, and so reducing the cross-sectional area by 50%, so typically reduce shrinkage reinforcement by 50%. This is a flat slab construction. This is on an 8 by 8 meter grid. It's a 270 thick flat slab with little continuity, so it's quite thin. So you can see the plank being installed. It's got the open sides for forming the joints. So the bars are slid across into those joints, and then those joints are filled up with concrete. This is the project in India Scott mentioned, where we did a part of the building using Robovoid. So we just sent the product to India, and a local precaster could use the product, and it was a good demonstration of anyone being able to use it. Closer to home, this is a factory in Geelong, where we used it for some factory wall panels. We were able to reduce the amount of deliveries to site for this job using the product, and the panels, some of the panels were also acting as retaining walls when there was backfill introduced. Here's an in situ ground slab application for our infrastructure project in Melbourne, a level crossing removal project. So instead of, I guess, polystyrene waffle pods, we can use it on the ground and pour concrete over the top. So we've done a lot of testing on that product with Swinburne University and RMIT at the Smart Structures Laboratory. We've done all sorts of tests. We've done bending, pull-out, compression tests, shear tests, all sorts of things. We've done some quite large-scale fire tests. This is a 3-story facade fire test, and this demonstrates that the fire just self-extinguishes at the end of the test, and it doesn't spread up the facade like the type of disaster that you'd be familiar with that happened in the UK a few years ago. I forget the name of that one for the moment, but yeah. So we've got compliance there. We've also done floor fire testing. So underneath this test, there's a furnace. So this is a standard floor test, fire test. And we're aiming for a 2-hour fire rating, but we got 4-hour fire rating. So that was very good. So this test actually includes 4 panels joined together. So the joints are actually tested in the fire test to see if they are the weak parts, but they performed well. And then the yellow test rig on top is applying 15 kilopascal of loading during the test. If you're not familiar with these fire tests, the fire in the furnace goes up to, I think, about 1200 degrees Celsius. So it's quite hot. This is a load test on a flat slab construction, the slab I showed you before. The way we applied the load was by filling up some swimming pools on top. So there's about 56 tonnes of water on the slab, which represents the ultimate limit state. And Swinburne University monitored the performance. The maximum mid-span deflection is 14 millimetres. And when all the load was removed at the end, the residual deformation was about 1 millimetre. And then we get the question, what happens at the end of life? So we demolished the slab structure and demonstrated that we can separate our product from the concrete. So it's not like polystyrene. When you demolish the structure with polystyrene, the polystyrene will just disintegrate into millions of pieces. Our product largely retains its integrity, and you can separate the reinforcement and concrete. It's a bit of a manual process in terms of pulling the plastic out, but it's the sort of thing you only do every 100 years, so it's not too bad. So all this research has helped establish a design guide, which provides guidance in terms of Australian standards as well as international standards. That's got things like load span tables and typical details. The projects we're currently doing, we've got quite a few infrastructure projects coming up in Victoria. The market seems to like it in retaining walls, so we've got a few retaining wall projects coming up for Northeast Link and level crossing removal projects, and that's in the precast elements, and also for the in situ slab, connecting some of these elements, and so we're getting very good concrete savings on those projects. We've been exploring opportunities in Saudi Arabia for some construction. We've done some trials over there in a precast factory at Prancer Precast, which went well. And there's quite a lot of interest in the UK now. I think some of you probably quite aware that in London they're quite focused on sustainability, and the previous presenter was talking about some of the initiatives over there. So this is a proposal for a large central London project. So that's where we're reducing the amount of concrete by 30% and speeding up the program by a factor of 2. I forgot to mention that the concrete we use with our product can be sustainable concrete as well, using some of the mixes the previous speaker talked about. So not only do we reduce the amount of concrete by 30%, but what's left over can also have a cement replacements in it. So you could have 30–50% cement replacement in what's left over. That's a job we did a scheme for in Melbourne, 30-storey building, office tower. Some work on volumetric construction, retail, data centres.
Sorry, John. I think Evan's kindly giving us the wrap up. So,
yeah, I think I'm finished. Yeah, okay. This one's for the Amazon guy. And but just to finish, the system is very versatile, as I think you've seen. You can use it in floor and wall elements, and versatile, sustainable, fast, efficient, and achieves quality construction.